Okay, so this is Psych 522, and it is October 8th. What did we do last time? Well, last time we talked about cross-validation, and we also finished up discussions of MANOVA and discriminant analysis. When we got into cross-validation, remember what the big picture was, okay? So the big picture was that we have a trained data set, right? We have a trained data set, and we have a test data set. And we divide the data set into parts. And part of the big picture of last time was that you may train the model on a particular data set, but that what really counts is that when you test it out. Okay, so the test data set is in some sense, the ultimate validator to the trained data set. Okay, we came up with some analogies for that as well as to how that makes sense, even in terms of like clinical applications and things like that. You can have a good theory on one person, but it's maybe only as good as you test it out on another person or another population or what have you. Okay, so the idea of theory building here is kind of paramount to all these concepts that we're talking about. And what we want to remember is that the concepts that we're talking about, though they are statistical, they really do have those wide applications, and you can draw analogies to other places where you actually follow this logic, because this logic of training and testing is evident in a lot of different places. So the idea of cross-validation was to estimate this test error rate, right? You want to estimate the test error rate, and we wanted that test error rate to be as low as possible. So whether you select a large sample for validation, or you even choose one particular object or unit, you can have various sizes, and that's what we talked about last time. Now, what we're going to talk about right now is also in this chapter, but it's a little bit different than the techniques we have been talking about. So this is called the bootstrap. And the bootstrap technique is mostly used when you want to estimate the variability of a parameter, okay? So it's really good for estimating the variability of parameter and for also estimating a parameter itself, okay? Now, we're gonna see it used often in terms of estimating standard errors around a parameter and things like that. So that's going to be a very, very common usage. And we're going to talk about that a little bit in this example right here. Now, what's the big picture here? The big picture, as we should always ask before we look at any statistical method or do anything, right? Remember when we did the MANOVA, the biggest question was, why would you want to do MANOVA in the first place? And the reason for doing MANOVA was definitely not because we had more than one dependent variable, right? So when we were looking at the MANOVA, we didn't just say, because you have more than one DV, then you should do MANOVA. That would be absolutely wrong. These dependent variables had to some sense go together. Otherwise, it's a completely exploratory search. If you're just kind of picking these at random or just kind of joining them from different research labs, MANOVA is most likely inappropriate. It's a waste of time. It's not going to make much sense. But if these variables seem to go together in some kind of theoretical way, at least, or some kind of hypothesized way, then doing the MANOVA may be a possibility that you wanna give it a try. Okay, but again, there should be a rationale for doing it. Now, what we're going to talk about later in today's lecture is the idea of the linear combination. So we said this is a linear combination, and we're going to be talking about a very specific linear combination in principal components analysis, which we'll develop further. But just to kind of let you know where we're going is this was a linear combination, and we're going to be talking more about linear combinations. The bootstrap, however, is not related to stuff like this. Okay, it's not related to stuff like this. And though it's related to cross-validation, as I said, it's a little bit different because we're often going to use it to estimate parameters. So what is the bootstrap? Well, it's to quantify the uncertainty associated with a given estimator or statistical learning method. Okay, that's going to be the primary use of the bootstrap. Now, why would you want to do it? Well, let's think about what happens when we compute standard errors. Okay, so I may have my mean distribution here. Let me just draw a sampling distribution of the mean. So there's the mean of all means is equal to the mean. Okay, so I'm just doing a sampling distribution of the mean. And we know that the standard error of that distribution is sigma over square root of n. Okay, so there's my sampling distribution of the mean, whatever we're drawing that for. Maybe we're drawing it for IQ, maybe we're drawing it for something else, but that's the sampling distribution of the statistic, right? Of the statistic. The statistic in this case happens to be the mean. So once I draw this in, I'm going to have my standard error bars, right? That should all make sense as to what we're doing here. We've got all these standard error bars, and that lets me know, the function of the standard error lets me know how much variability I have around expectation, right? How much variability I have around expectation. Now, in previous stuff that you've done in different courses, you've learned that this sampling distribution can be constructed. Now, it could be constructed based on what? Based on theory. Based on theory, right? Nobody constructs sampling distributions with real empirical data, unless it's for a simple like teaching example, but nobody really builds sampling distributions based on real data. Why? Because we're talking about n upwards of infinity, right? So remember, the logic of the sampling distribution is that if I reach back into the population and collect a sample of say 25, well, I'm going to have to keep doing that. The number of samples, okay, the number of samples, not necessarily the size of the sample, the number of samples. Let me make this a different n then, just a bigger n. The number of samples should be infinite if this is actually going to be a sampling distribution, right? Because I'm repeatedly going into this distribution and I'm gathering means from it. So I'm repeatedly doing that. How often am I doing it? I'm doing it an infinite number of times, at least in theory, right? The theory says do it an infinite number of times based on a sample size of a particular number. So I can construct this sampling distribution, and via constructing the sampling distribution, I can have a pretty darn good estimate of what this is, right? I can have a good estimate of what this is. Now, this is the standard error, but I usually don't know what the standard error is, right? I don't know what this is. So I have to use S in its place and get the estimate of the standard error, right? I have to get the estimate of the standard error. Otherwise, if I have sigma, then technically I have the standard error. So I usually have to get an estimate of the standard error. Well, when we do that, we are relying on theory development. And we say that we are doing this analytically, okay? So we're doing it theory, we're doing it analytically. Analytically. Okay. Analytically means basically theoretical. It means developments in mathematical statistics tell us what that sampling distribution should look like. Here's where the bootstrap comes in, okay? So the authors don't kind of provide you with that context to get us started. That's what I'm trying to provide here, is why even want to even contemplate the bootstrap? Well, the bootstrap is useful for quantifying the uncertainty. We just quantified the uncertainty here in our sampling distribution, right? We just quantified the uncertainty here. The bootstrap says it can also quantify the uncertainty. So what does the bootstrap do that this doesn't? And the big differentiator here, the big difference between these two approaches is what? You know, what's the big picture? The big picture is this. Take out the theory. No more analytical derivation. No more analytical derivation. We are now going to do this in a basically non-parametric way. Okay, we're going to basically do this in a non-parametric way. And when you think about non-par, you're you're thinking about the idea of no assumptions. Okay, no assumptions. When we developed this sampling distribution, we had to make some assumptions. We had to invoke the central limit theorem and that kind of stuff, right? Remember, to get the normality, right? Remember when you first draw that sampling distribution, you think, how do you know that sampling distribution is normal? Well, we got the CLT, right? The central limit theorem tells us that that's going to be approximately normal as your size of the sample increases, okay? So that's, again, based on theoretical assumptions. It's based on analytical derivation that we're actually able to construct something like this. So the bootstrap comes in handy when you either don't have this, right? You don't have this, you don't have the theory, or you don't want to use it, okay? So there's kind of two cases where you might want to bootstrap, is when you don't have the theory or you simply don't want to use it. And what the bootstrap does is the bootstrap takes advantage of computing power. Okay, it takes advantage of computing power to basically resample, okay, resample. Okay, so resample. Okay, that's why, you know, when they talk about the title of this chapter, they talk about resampling techniques. When you think about those validation techniques that we looked at, they're not quite in the same spirit of resampling, right? We weren't really resampling anything. We were just kind of dividing our data set into the train versus the test. It wasn't really resampling. But when we talk about the bootstrap, it really is resampling. Because what you're going to do is you're going to take that population, right? You're going to take that population and you're going to resample from that population. Now, why would you want to resample from the population? Well, let's do this. That's not underlining. That's just trying to get the arrow over here. Okay, I wasn't trying to underline that sentence. We've got our population. What did we do over here? We resampled, right? We resampled in order to get the sampling distribution of the mean. We resampled. Now, we didn't literally do it. We did it based on theory. So remember from previous courses, the idea of I'm going to go back into the population, I'm going to sample and produce a whole bunch of estimates. That was based on theory. Well, thanks to computing technology, which is basically speed in terms of what we're talking about. We're not talking about something mysterious. We're not talking about something that only a computer can do. You can do this. You can do this kind of empirically and manually. It would just take forever. We are going to actually go back into the population just as we would theoretically. There's the population of all the objects. And we are going to do this process. We're going to do this process that we did here if we're doing it for the mean, right? This is the sampling distribution for the mean. We're going to go into the population. We're going to do this process, but we're not going to do it theoretically. We're actually going to do it in quotes for real. Okay. So go here and resample, right? And make it reality. Okay, make the resampling reality. Well, how are we going to make the resampling reality? Okay, well, you could, like I say, do it empirically, and it would take you forever to do it. And you would go back into the population and keep resampling forever and produce your sampling distribution. That's not very practical because you're gonna run out of your generation. You have to go to the next generation and keep doing it. So it doesn't work, right? What the computing technology allows us to do is go into the population, and let's say we're going to sample instead of an infinite number of samples, right? Instead of an infinite number of samples, let's get, I don't know, maybe 1,000, right? Let's get maybe 1,000 samples. So let's resample 1,000 times from the population and mimic, okay, mimic this process right here. We're going to mimic the process. That's what bootstrapping is about, or at least it's a very, very common use of bootstrapping. So when you're trying to estimate uncertainty around a parameter, and how do we measure uncertainty around parameters? We compute things like standard errors. We use that to compute things like confidence intervals. So if this is the unknown parameter, we want a little bit of a margin around it. We want that uncertainty so we can kind of estimate where that parameter actually is. There's the difference, is that with computing technology, we can say, well, let's go and resample from that population, from the mimicking the population to get this over here. Now here's the problem here. Now I'm calling this a population, right? I'm saying that bootstrapping goes into the population. But here's the problem. There's a problem with this because we can't literally go into the population, right? We can't literally go into the population. For what reason? Well, usually we can't because we only have sample information, right? So usually this is unknown, right? We don't have the population. But look at it this way first. Wouldn't that be the best case scenario? That would be the best case scenario for this idea of bootstrapping. If we're going to resample anything, the best case scenario would be going into the population of units and resampling. That would most closely mimic this process, because this is kind of like the best, right? This whole process here, you can say this is kind of like what we're trying to approximate. This is the best case scenario because it's based on theory and it's based on an infinite number of samples. So the best case scenario for bootstrapping would be going into the population and getting all those resamples. But we can't do that. So that version of bootstrapping isn't going to work, right? And we got to tweak it a little bit. But recognize that that would be the best case scenario. If you can't do this, then resample from the population. That would be nice. But we can't do that. So we even have to go to the third best option, right? Remember, statistics is all about approximating. Statistics is about kind of saying, well, if we can't do this, well, maybe we can do this. What's the third best option? Third best option is there's your sample. That's all I have. That's all we have. All we have is the sample. That's not the population unless it is the population, right? If your sample is 100, right? If this sample size is 100, that's a sample size of 100. Well, that could be a population as well, right? If those are the only units we're interested in studying. If those are the only units we're interested in studying, then my sample is my population, and I don't have any uncertainty. So I don't even have to be reading this part of the book, because then I just get my estimates from whatever that says. Right? So then I actually know what my population mean is. Right? If this is all I'm interested in which case it's the population, and it's equal to 100 observations. Now that doesn't mean I won't have measurement error, because I could still have measurement error, but that's a little bit different than this idea of getting the estimate on the uncertainty in terms of standard errors and things like that. Okay, so we have to realize that those are two different processes. But here, I'm going to assume that this is not my population. I want to know more than this. So I legitimately call this a sample. This is a sample. So I can't do this. I can't do this. One other reason why I can't do this is sometimes we don't know what those analytical expressions look like. And that may seem weird at first, but there's times when you're computing different statistics where you don't know what the standard error is. The standard error, the mean, is well known. Everybody knows what it is. It has really good theory and things like that. But again, we had to make a whole bunch of assumptions of what type of population we're sampling from, right? Normal population, central limit theorem, and all of that. But there's many times where you actually have to sample, where you actually, it's not that you're not uncertain about the assumptions, is that you don't even know what the closed form analytical expression for the standard error is. So this may be a completely unknown. You may not even know the formula. I'm not talking about just what these values are. I'm talking about, like, as analogy, you don't even know what the thing is. You don't even know what the function is. Okay. So in that case, this approach has a lot to lend to it. Because if you don't know what the closed form analytical expression is, wow, what if you can just continuously resample and just compute the standard deviation of those estimates. So you may not know how to compute the standard error, but you can just get the standard deviation of the estimates you do get from the resampling. So recognize that this approach here that we're about to look at, it's kind of, in a sense, it's kind of advanced because you need computing technology to actually carry it out to make it even practical or feasible. But on the other hand, it's kind of rudimentary in a way, right? It's kind of rudimentary because it's kind of like we're going back to the days where we didn't have the theory. So imagine you're doing an experiment like in the 1800s or something like that. You'd probably try a version of this because they didn't have the theory developed back then. Okay, so you've got your sample. How about we go into the sample and we select samples. Okay, we're going to select samples from the sample. So you have sample 1, sample 2, sample 3, sample 4, etc., etc., etc. How many samples? Maybe I have like 1,000 samples, maybe I have 500 samples, maybe I'll choose a lot more. And then what am I doing with those samples? I'm able to look at the variabilities of what I'm getting in my estimate, right? I'm able to look at the variabilities of what I'm getting in my estimate and estimate how much uncertainty I have around the parameter that I'm estimating. Okay, so look what I'm doing. I'm sampling from the sample. Best choice in the bootstrap sense would be to sample from the population. Right? Remember my population up here? That would be the first choice. That'd be, that'd make a lot more sense. Sampling from the sample seems like a desperation move, and it kind of is. That's my point. That's kind of my point of saying, if you don't have any closed form analytical expression, just sample from the sample if you can't sample from the population. So I'm sampling from the sample and I'm getting some estimates of variability. Now, if you look up here, where we're going to use it, bootstrapping, to assess the variability associated with the regression coefficients in a linear model. So we're going to get, when you get regression coefficients, you can develop potentially some standard error estimates around that coefficient by the bootstrapping. And again, times you want to do that, especially is when you don't know if the assumptions hold and you just want to try the bootstrap method to get that variability. So that's the big picture. That's the big picture of what bootstrapping is about. I can also tell you that bootstrapping is becoming pretty common, and largely because of the computing facilities, the computing power, that you can actually do this. Now, you can point out some weaknesses of it, right? You can look at it, ask yourself, what do you think of the method? What do you think of the method, right? Well, you're sampling from a sample, and this sample that you're getting, it would be nice if these were random samples, right? Because you have a sample and then you're getting a whole bunch of samples from it, and it would be nice if these were random. Okay. Now, in theory, we're getting randomness. Okay. In theory, when we do the resampling over and over and over, we are getting randomness. Here, this isn't really random, right? Because you're actually having a computer select random samples. So the computer actually isn't computing a definitively random samples, not how we would think about it in the theoretical. It's computing what would be called a pseudo random sample. But for all purposes, we're going to talk about it like it's random. But just recognize it's not quite as, what's the word, right? Pristine. It's not quite as pristine as these ideas here where you're doing theoretical random sampling. Here, you're sampling with a computer, therefore it's not entirely random. I mean, it's close enough, but it's not entirely random. So the example that they use here is not particularly interesting. They're looking at yield returns of X and Y, where X and Y are random quantities. So they're putting a fraction of the money into X and will invest the remaining into 1 minus alpha into Y. So they're saying that there's variability associated with the two assets, and they want to choose the fraction to minimize the total risk or variance of our investment. So they want to minimize this quantity here. Well, they can show that for this particular example, this formula is not important. Okay, this is not like a general statistical formula that is relevant to bootstrapping. This is just the function that they need to compute to get this particular value for their example. And here are the different inputs to that formula over here. So really this parameter here, you can think of this as being like a population mean or a population median or some other parameter instead of this like complicated function right here. The point of what they're talking about here is that we don't know these values. Okay, we don't know these values in the function. And that could be true for any particular parameter, right? We don't know what the function values are. So we have to, as usual, we have to estimate them. So there's our estimates with the little hat values. How do we estimate it? Well, maybe use a data set that contains past estimates for X and Y. And then you can estimate the value for that parameter. So that's what they're doing there, is just plugging in those estimates and getting those particular values. Now, figure 5.9, as we'll look at in a second, let me just tell you what it's going to be about. This approach for estimating alpha on a simulated data set. Okay, so this is going to be on a simulated data set that we're looking at right here. So each panel displays 100 simulated returns for investments of X and Y from left to right, top to bottom, the resulting estimates for the fraction, which is our parameter, right? We're trying to estimate this value. So that's why they're computing this based on the estimates input into it. And these are the values we get. Okay, so let's look now. They obtained 1,000 estimates. Okay, they obtained 1,000 estimates for the parameter, which they're calling, but with the hats on it, right? With the hats. And the left-hand panel of 510 displays the histogram of the resulting estimates. Now, let me just tell you what we're going to be looking at here is you're going to have the mean estimate right here, and then you're going to have a standard deviation of the estimates right here. So they're computing a standard deviation, and you can see how they're computing the standard deviation, why this kind of makes sense as to why it's the standard deviation. There's your n minus 1, right? There's your kind of like the mean minus the mean idea over here, because you have your squares. I'm kind of simulating like the idea of doing the numerator of a variance here. Okay. And let's look at that graphic. So when they're saying the accuracy, right? The accuracy is the standard error is approximately 0.083. So for a random sample from the population, we'd expect the parameter to differ by about 0.08 on average. Well, let's look at their diagram here. So left, we have the histogram of the estimates of the parameter obtained by generating 1,000 simulated data sets from the true population. So what's the idea here? This is based on the true population. Okay, so what they're kind of emphasizing is that this is true. This is our best shot at the truth by generating 1,000 simulated data sets from the true population. Now that's as much truth as we can get here in terms of not being completely analytical or theoretical. So they're kind of doing a resampling, but it's the true population. If you look at the center one, these are estimates of alpha obtained from 1,000 bootstrap samples from a single data set. So remember I was talking about on the previous page, what did I say that the first choice was? Well, the first choice would, or the most kind of like the ideal choice would be to know all the theoretical assumptions and know your theoretical population and to do it that way. The second choice is this one, okay? The second choice is this one, because that's exactly what they're doing right here, is they're doing 1,000 simulated data sets from the true population. Okay? From the true population, so that's what I mean, true is the population right here. And this is what they get. This is the estimate they get right over here for the overall average. But again, this is first choice. Well, we can't do that, but since it's kind of like an ideal, and is exactly what the authors are doing here, they're saying, well, there's a first choice. Well, we can't do that. Okay, now we're going almost to that third choice, right? I'm saying, well, all right, let's just bootstrap something. Well, this is 1,000 bootstrap samples from the single data set. Okay, 1,000 bootstrap samples from the single data set. So this particular graph here is what I just draw on the other page. There's my sample. This one here, what should I write? Population. First choice, second choice. Bootstrapping, samples from the sample. The best way, or at least nearly the best way, is to sample from the population. So you see the difference. Now, what they want to show here is this is all simulation too, right? You're not doing this for real. Like when we say this is the true population, we're not doing this empirically. This is all simulated stuff. Right? This is all simulated stuff, but it's kind of used as the ideal in this example. So how close are they? Well, they actually come out to be pretty close. So in other words, the bootstrapping is actually pretty close to the mark, as they show here in the box plot. There's the parameter, there's the truth. There we go, that's better. So true, and then you've got the bootstrap over here. So you can compare the two and say, well, the bootstrap, okay, so the median is a little bit lower here than the truth. Right, there's the true value of the parameter. This is based on kind of sampling from the population, and this is sampling from the sample, which is the bootstrap. And you can see that they're relatively close. They're going to be a little bit different. And you also get like a little bit of outliers here, a little bit over here, but still relatively close. Still relatively close. Okay. So we can also compute the standard errors of these coefficients, and that's what they're doing over here. So I said that you can compute standard errors. You can compute the variance of these estimates. The sampling is assumed to be performed with replacement, and you get those estimates of how much variability you have around the parameter you're estimating. So they do a nice, this is like a really nice figure. It's a really good figure to show in a very small scale example of what bootstrapping actually is. So there's your original data. Now, let me just redraw my graphic from earlier. What would be the ultimate idea here? Well, the ultimate idea would be that this is not sample data, right? That would be the best. If this was not sample data and this was population data, that would be like really good, right? So if this was, let's just put this for a second and say this is population. If this was population, getting your different samples from the population and getting estimates of the parameter would be the best case. So again, we go down to our almost a third choice, right? The third choice is saying, well, you don't have the population. Because, if you had the population, you probably just measure the parameter on that population, right? So think of it, right? If you had population data and someone said to you, hey, let's bootstrap from that population. You say, actually, I just want to measure the value of the parameter. So why don't I just compute this on the population and be done with it, right? If you actually have all those units. Now, let me just develop that point a little bit, because that could seem a little bit confusing with the original analytic approach we took, right? So what I just said is that if this is the entire population, just compute this and you're done. Like there's no reason to do sampling like this from it. If you actually want to know this and you have the whole population, you have all of those units, like maybe there's 1,000, compute this, that's the value you're trying to get on the 1,000. Well, sometimes you don't have the information of that function, as in this example, they didn't have those values, right? They didn't have the covariance of x, y, they didn't have the variance, they didn't have those details. So in their theoretical example, they're kind of estimating this because they have some unknowns. But let's imagine you could just compute this like you're computing a mean. Then you just compute on the 1,000 and you're all done. Now contrast this idea here to the theoretical idea, the analytical approach, the first example that we looked at with the sampling distribution of the mean as one possibility. That was just one example of computing a statistic. What's the analogy between this approach here and this here? Well, in this particular case, I'm pretending like I know P. I'm pretending like I know the population. In this particular case, the population is completely unknown. Right? I just don't know what the units are in that population. So here, when I'm doing the theoretical approach, you know, when things are developed analytically, you have to actually produce a sampling distribution because you don't know what the population is. So in this contrived situation here, where you would actually have the population, you could just compute the parameter if it's feasible. But that's not what they're talking about here. So when they're talking about here, they're talking about the original data is not a population. It's a sample. Okay. That's where the bootstrapping idea truly comes into vogue, because you're going to basically treat the sample as what? What are you actually treating the sample as, just for the sake of bootstrapping? This sample becomes your intermediate population, right? It becomes kind of like an intermediate population because you're going to sample from the sample. So we're giving a lot of respect to the sample here, right? We're giving a lot of respect to the sample because we're saying, okay, let's pretend like this is like kind of like all we have. So let's kind of pretend like this is population for a second, and then let's sample from that population. So again, to emphasize why this is that I keep saying it's, boy, that's almost like your third choice, because you're down to sampling from the sample. And that's exactly what they did here. And they sampled with replacement. They got the different observations, and then they can compute estimates on what that parameter is. And then they can compute so you got different estimates of the parameter, and then you can compute how much variability do you have around the parameter. So imagine this idea of producing the sampling distribution. If we were to do this analytically, what would this look like? Right, the mean of, what do I want to do here? I want to do the mean of all of those things, right? The mean of all of those things is equal to the mean. This is the idea. This is the thing we're trying to estimate. When we develop the sampling distribution of the mean, this used to be this. That's the same idea. And then the standard error, well, that's what they computed on the previous page to get the variability of all of these things, because each one of these bootstrap samples will not give you the same estimate. That's why these are different from one another. They're not going to give you the same estimate. This is for the how many bootstrap samples we're taking. So they won't give you the same estimate. So you'll have like one estimate fall here, one here, one here, one here, one here. And look what you can do. You can say, hey, how much variability do I have? How much variability do I have in these? And then you can estimate that variability. So that's why I said at the beginning of this discussion, I said, you know, like bootstrapping is used to estimate parameters, but it's also used to estimate kind of like that uncertainty around parameters. And really, when you think about bootstrapping, the primary focus, we usually don't think about in terms of like estimating the parameters. We think about more the uncertainty of the parameter. We want to know the uncertainty of the parameter. So if you're getting bootstrap samples from here, and you're getting wildly different estimates, like this is equal to 10, this is equal to you know, 1,000, etc., then you've got a lot of variability. So that's the idea behind bootstrapping. With replacement, but again, remember, it's with replacement, you're still sampling from the sample, and you're taking random samples. This should be random, but it's not really truly random because you're using a computer to generate that information. But it's, I mean, as close as we can get, other than trying to develop a truly random process. But that would take too long to kind of, you know, start flipping coins and stuff like that. So the computer is well sufficient for doing this. And the nice thing about the computing power, again, is that you can get a whole bunch of bootstrap samples. You don't have to stop with like 1,000 or what have you. You can get 5,000, you get 10,000, etc. bootstrap samples. And you can even adjust that when you have to do bootstrapping. You can try 500, you could try 1,000. You can also see that if you're sampling a lot of observations, this procedure could actually get, you know, quite intense in terms of the computing power required to do bootstrapping. So it's a pretty computing intensive approach, especially if your numbers are pretty big. Okay. Now I just want to end this section here just by talking a little bit about these big differences. Is the bootstrap, you know, they could have developed the bootstrap 200 years ago. It's just that nobody would have done it because it just takes too long. So you think about, you know, what's the best approach? Well, back in the day of when theoretical statistics were being developed, most of this stuff was being done analytically. The analytical derivation is kind of, in a sense, it kind of saves you a lot of computing work, right? A lot of calculation work. Because if I told you that the sampling distribution of the mean has a standard error of sigma over square root of n, wow, you don't have to do all this, and the computer doesn't have to do this because we know the analytical formula perfect, and this is derived from good theory. This didn't just drop out of the sky. This is derived on analytical argument, on theoretical argument. So you can think of the analytical approach as, in a sense, a little bit more of a cleaner approach, but you have to invoke assumptions. When you can't invoke assumptions, or you don't know what this looks like in the first place, as I mentioned, sometimes we don't know what the standard error even looks like, right? Then you have no choice. If you want an estimate of what that sampling distribution looks like and the variabilities of your estimate, the bootstrap is a really, really nice idea. Okay, so that's it for the bootstrap. Why don't we take a quick break? We'll come back and we'll start talking about chapter 6 on model validation and model selection. Be right back.